Thanks everyone for coming back. And I put up here a quick summary of some of the things we ended with to get us started really quickly. So remember, we decided to work with orthogonal polynomials, orthogonal defined thus. They have a recursion relation, and you can rewrite the partition function entirely in terms of those, because you build the key thing is the van der Waals determinant. You build that out of PNs. I should mention, I don't know if I'll get to why this is important, but I should mention that you end up using the first n orthogonal polynomials in doing so, starting from n equals 0 to n minus 1. That's going to be, that may be important later on. Then I have the examples we looked at where we, knowing the potential tells you the RNs. We derived a formula for that, which I haven't put up here, but we then put in a couple of examples. This is the familiar, perhaps unfamiliar normalization, but familiar for what you get if it were the Hermite polynomials in the Gaussian case. And this is the case of lambda to the 4. And I put that there, although I won't do as much development of that case. I do want to show you what happens for some of the higher critical versions of the story, where you have, with the lambda to the 4, you have vertices, which means you'll be able to tessellate with squares and actually have two-dimensional gravity with finite area. But we will spend most of our time showing how some of the techniques work in the simplest case, where you don't have that, but from the point of view of them being matrices, and for us really focusing on the matrix origins of a lot of the physics that we're interested in, it won't matter that we're using such a simple model. Okay, so I want to take the large n limit now, and we do just what we did before. We have x. We'll define a coordinate x, then over a capital N, just as we did before. And things that have an index n will then become functions of x. So you see then Rn will become some function I'll call R of x. And I had written things in a particular way, pull the ends out in such a way so I can then easily convert that into an integral. And so I have, and then I'm going to be interested in the free energy, the connected diagrams for the gravity problem. So I'm going to have minus a log of this thing here. I think I'll still put a tilde on this. And so I'll have minus n squared. There'll be an overall factor, which we won't worry about. Integral from 0 to 1 minus x of log of r. X dx is the thing that we need to study. And so the interesting behavior is going to be coming from the neighborhood of, well, I have two interesting things going to happen. I have x can go to 1, which will be telling you about one of the endpoints. And also, I could have R doing something interesting as well. And so I'm going to try and focus on those two things. And it's those two things that will be the analog of what we said before, tuning to n large and finding interesting behavior. And so let's see what that interesting behavior could be. So there's actually not too much interesting behavior in the simplest case compared to some of the things I wanted to talk about. Rn in that case is just x, and it just goes to 1. Let me jump immediately to this case. So at large n, the difference between the different r's is not going to matter. There will be corrections to that later on that will matter, but right now what we can simply do is to set them all equal. And then we have a simple equation, which is just 2r plus 12 G4 R squared is equal to X. So, so I can solve that. And so I have -1 plus or minus the square root of 1 plus 12 G4. And before we do anything fancy, let's just observe that this is already something kind of nice. I could substitute this back in. I could, for example, expand in small g4, continue doing the field theory. I could expand in small g4 and plug that in, plug that into there and get some numbers out, powers of g4 with coefficients in front of them. And that will correspond to having started with the matrix model and drawn those Feynman diagrams we talked about. And you'll see it'll start enumerating all the Feynman diagrams that you can draw on the sphere. And so it's a fun game actually to match those numbers and actually see how that works order by order as a nice nice exercise. So that's a cheat. So that's letting us know that our methods are good, but we want now to do something a little bit more interesting. Remember, we want to tune so that the Feynman diagrams that are large, that have a large number of vertices and hence a large number of squares or triangles or whatever we've built this thing out of, squares in this case, will dominate. Let's see how that goes. And you can see there's an interesting point. So in the neighborhood of x equals 1, there's an interesting point G4 going to -1/12, x going to 1 is an interesting point that I'm going to put my attention on for a moment and see what we get. So let's see. I wanted to say, yes, there's something else I want to pay attention to. There's another representation. So remember in the original setup, we solved the saddle point equation by going onto the complex plane and deducing that form for rho. Lambda, rho of lambda was v/2. And then there was some polynomial, and then there was the thing that came from the cut behavior, like that. And that was all very nice, and we had conditions on the function this came from that told us what Q was. So there's a different representation of rho that will actually be useful, which naturally comes from the orthogonal polynomial problem. And that actually looks like this. It's an integral representation. I think it first appeared in the second of the papers I mentioned, the Bessis et al. Paper. And it looks something like this. And I'm going to use that shortly. So you keep the real part. So you could put a theta function of this quantity up there if you like, to make sure you're only looking at the real parts. But I'll skip that. So, and I'll show you how that reproduces this in a moment. But this is going to be very useful. Its double scaled version is going to be nice as well. Okay, so let's see. What do I want to do? It's different things I can do at this point. Let me finish the job here. So what we can do is the nice way of dealing with this is to change variables from integrating over x to integrating over r. We have a relationship between x and r here, which I could call w of r. X is some function of r. And so then I can trade the integrating over x to integrating over r with a w primed Jacobian. So I'll have something like 1/pi, and then I'll have r at the endpoints 0, w prime of r dr over 4r minus lambda squared. So then I just need compute what W of R is. In fact, you can probably immediately see for the case of the Gaussian, R is X, so W of R is R, so that primed is just 1. And there you can see precisely this comes out. Yeah. More interestingly, perhaps, oh, right, I need to. More interestingly, perhaps, would be the case of the quadratic case, which will be useful. Just in case I'm wondering what I'm doing, I'm going to get funny behavior for R, the function R of X, and I want to see what that means for the spectral density. So that's why I'm spending a little bit of time on this, because that'll be intuitive, immediately tell you how things generalize. And in that case, then I have W. So for the case of with G4, the second case, second example, I have W primed is 2 plus 24 G4R, and then I just need to do this integral, 2 plus 24 G4R over the square root of 4R squared minus lambda squared dr. And when the dust settles, you get 1 over pi 2 G4 lambda squared plus 4 G4R plus 1 square root of 4R. And you see, it is what I showed you the other way, which is some polynomial. There's some polynomial. No, that's not right. I apologize. I realize I wrote something wrong here. I wrote the function. Not. Sorry, that was F. The resolvent, which I shouldn't call F on this board. You remember from last time. Eventually, it gave you rho. Rho was this. Sorry, that was a wrong equation. Good. So indeed, it's some polynomial, and that's what we got in this case as well. And you can see this generalizes quite readily in this form as well. I think I may have heard something like a question.
No, that was my fault.
Oh, okay, right, good. Okay, so I'll get to this in a moment, but you can already anticipate. Let's just go ahead and do it. If you stick G4 equals minus 1 over 12, which is the interesting point there, you'll see something interesting happen. This will become 1 over pi 1 over 6 4 minus lambda squared. You can pretty much eyeball it. 4 minus lambda squared, 4 minus lambda squared. So what's happened? Something interesting has happened. We have the Dyson behavior, which I've erased. We had the, what would be an e to the half type behavior on the endpoint. But I've got precisely, if I write this as 2 plus lambda, 2 minus lambda, I have precisely on each end an additional 0, which is something that's going to make that endpoint characteristically different in the scaling limit. Anything different from that would scale away and not give you anything new, but it's a random G4, but that particular G4 will change this endpoint behavior. And in general, it's going to be K minus a half, where this example is K equals 2, and the Gaussian example is K equals 1 in this notation. So that's what happens. So this is the kind of critical behavior. I think it goes back to Vladimir Kazakov, who realized that that should then correspond to what was at the time called multi-critical matter coupled to gravity. And indeed, that's that all pans out. So we've seen now, so we've generalized the Wigner case has gotten a little more interesting.
This is just pure gravity, no?
Yes, this, yeah, but I meant the K, more general K, yes, indeed. Pure K equals 2 is pure gravity, K equals 1 is topological gravity. Okay, good. So let's see what happens in the free energy when this zero, this extra zero lands on the endpoint. So I should be careful on time. Let's see if I can skip a little bit. Okay, I think I'm going to do the double scaling limit right now, which is to say I'm going to sneak up on this point by approaching these critical values with scaled values as follows. And I'll explain some of what I'm going to do a little carefully after the fact. So double scaling limit, DSL. And so now we're going to the late 80s, early 90s historically. Brezar, Kazakov, Douglas Schenker, Grosnick-Dahl, essentially all at the same time, observing some really nice things that can happen. So I'm going to say X is 1, but then there's a scaling piece away from 1, which I'm going to call X minus mu. And I'll explain exactly what I mean by that in a moment. X is going to be a variable, mu is going to be a constant. The meaning of that constant will become clear in a moment. R of X will be 1 minus some function, which I'm going to call U of X, as promised yesterday. I'm going to tell you what delta is in a moment. There's some scaling, some playing around typically with what you do, with what you end up doing. We won't need this just yet, but when we start looking at 1 over n corrections, we'll need a scaling for this as well. Actually, yeah, we'll need it right now. So 1 over n is going to be something which I'll call h bar to match the notation of the day. And it'll be a 2k plus 1. Now, so delta, as n goes to 0, delta goes to 0. As n goes to infinity, delta goes to 0. If you like, you can think of delta as essentially the typical size of one of those triangles or squares that you tessellated with, which is going to 0 in the limits that take large n. So the fact that I know in advance these powers is because I know those powers in advance, but you could put them in arbitrarily and just try and see what survives in the scaling limit. And it'll tell you that that's a consistent choice of powers to get finite physics on the sphere, and then it works on all topologies when you then work it through. So if you do all that, so you can basically take these scalings and put them in there and see what you get in the limit. And you get that f, and now I'll call it f without a hat, ends up being 1 over h bar squared, which is appropriate for being at the sphere level. Mu to infinity, x minus mu, u of x, d of x. So what we've done, we've zoomed in on that, essentially on that in the neighborhood of the upper limit of the integral. Now, it's worth stopping for a moment. I won't have time to go too much into detail on this, but there's a very nice intuition about some of the physics that I mentioned yesterday going on. Remember, the orthogonal polynomials, you can think of them as wave functions for every single one of the n lambda positions along the Dyson gas. And then so I can excite those in each of those oscillator problems and go all the way to, from n equals 1 to n. I don't know why I'm using the floor instead of here. Yes, right here. And so then what you see is that I'm scaling into an endpoint. Let's say it's this endpoint or this endpoint, take your pick. And I'm in the neighborhood here. And so that whole sort of x goes from 1 all the way up to n, that whole region here, the neighborhood of x equals 1. So I apologize, x goes from 0 to 1, and that's capital N going from 1 to n. That whole neighborhood gets blown up. And that's what this is. That's little x. And you can see that happening here. Little x goes from minus infinity all the way up to mu, covers that neighborhood. It is important to remember, if we were going to spend time in the non-perturbative discussion, it's important to remember that to fully non-perturbatively define the problem, you are solving, we will ultimately get a differential equation for u defined on the whole x line, which makes sense because that defines all of the orthogonal polynomials. We've only used some of them to define the matrix model quantities like the free energy, the first n of them, but there's an infinite number of them. And in order to define the whole family, you need the infinite family of them to be consistent. That's the way of thinking about when you have what seems to be non-perturbative problems with not being able to solve differential equations for u and stuff like that. It just translates to failing to find that complete set of orthogonal polynomials. So you could then do something else and use different boundary conditions and maybe find them. But that's looking ahead. And I'm just letting you know where all of that sort of technology you sometimes see in papers actually comes from. The other way of thinking about this is that it's a many-body problem. So I'm exciting each fermionic system with different PNs. That's there, and then I do that up to some level, some excitation level, and that's what this is. So this is also could be thought of as a Fermi energy. This turns out to be equivalent to a many-body fermion problem. The fermionic nature comes because of the presence of the Fredholm determinant. Yes.
Quick question. So when G4 is negative, then the original integral is not well defined because the potential is unbounded from below. I assume probably one needs to change the integration contour.
It depends. Sometimes, well, as you scale into the neighborhood, it may or may not produce problems for you. It turns out precisely what you're talking about becomes a problem for k equals 2. So k even in general, and that's the source of the instability that you often hear about. That's a longer story than I have time to go into.
The recursion formula for the polynomials is not even the orthogonality condition for the polynomial, right? Doesn't V appear in the orthogonality condition for the polynomial? So V is unbounded from below.
I mean, it indeed translates into problems for R through being problems for U.
But this can be made precise.
Yes, but just lack of time. There's a whole beautiful set of stories to be told there. I apologize for glossing over that.
But the simplest statement you might make is that there's no problem to any finite order of perturbation theory.
Yes, that's very important. To all orders in perturbation theory, thank you. Everything is fine. Yeah. Sure.
I thought that the idea was to define things not perturbative.
Yes. So there's a longer story. As I said, it's not always a problem. Precisely K odd is just fine. What it turns into is what looks like an instability of eigenvalues wanting to tunnel out of where you thought they were and maybe start an additional, the assumption that you had a single cut needs modification. There's another cut that they're and so there are techniques for then going in and computing the effective potential of one eigenvalue and seeing whether it's stable or not. And for K odd, it's stable. Yeah. There are ways of fixing that, which you actually have to do in order to understand JT. I'm not going to talk about that today. There's actually, I think, an hour-and-a-half talk I gave fall 2020 here at the Institute where I go into detail about how that works. So I'll refer you to that in view of time. Sorry. Okay, good. So, but I wanted to get those key elements out. So this is the result. Another way this is often presented by taking a couple of derivatives. You can also think of this as there's this function, and it's the second derivative of f with respect to x at x equals mu.
I thought even for K odd, the one cut distribution of eigenvalues is not non-perturbatively stable.
No, it's fine. Yeah.
I mean, the potential is like minus 5 to the 4 plus 5 to the 6. So if you have a 2-cut one, maybe I'm not. What you're discussing is just call one cut.
Yeah, for K odd, you end up with, for example, for K equals 3, you'd end up with something which which looks like the Q, you know, the K equals 1. I'm going to get to this in a moment. K equals 1, U is just minus X. And K odd just looks, and you can find, let me actually say this a little bit more carefully. This is X, so this is minus infinity goes to some mu, and so you want to have some, for perturbation theory, talking to what Edward was saying, for perturbation theory, it's enough to know the function u in this regime, and then I integrate from minus infinity up to mu, whatever that is. Typically, for the kinds of JT type problems, mu is usually, say, 0, and then you're good. And whether or not this function is doing something weird in that other region is a non-perturbative issue. It doesn't affect perturbation theory. So what actually ends up happening is that for for K equals even, this completion is not possible. For K equals odd, it is. It's not the only way of doing it, but there is one way. That is one way it is consistent. So you can actually find a sensible differential equation for which you can find a solution for K odd in all odd. Okay, I will not have time to talk about that today, but it is a very important issue. It is using techniques like that, and you can see how powerful this formalism is, because it allows you to visually, knowing the form of U, which is implicitly knowing the form of the matrix model potential, or almost explicitly, you can immediately see where non-perturbative problems are going to come from in precisely the language I just used, which is why I use that language in my papers since 2019 to formulate non-perturbative completion of JT. But I won't have time to go into that in great detail, except to remind you that it can be done, and I'll use the results of that.
Let's go.
Okay. Yeah.
Quick question about it. That formula for you, just to clarify, you meant the derivative with respect to mu and then said mu equals to F?
Thank you. Yes.
Okay.
Yeah. Thank you. Yeah. So one way of thinking about it, we'll just check. Mu is the thing. I'll do a computation just now. We'll see mu, at least in a unitary theory, is indeed the cosmological constant of the theory. So it's a thing to differentiate with respect to find out what the expectation value of area is. And indeed, so U then ends up being the 2-point function of the operator that couples the area, and it's often called the puncture operator, and then the 2-point function is the string susceptibility. So that's some language you see in some papers that might seem very mysterious. That's where that comes from. Okay, let me just go ahead and do this. I'm trying to make sure I don't lose. Okay, I've used this now. I don't think I'm going to use this again. So let me try and use this board. So I've done this. I don't think I need that. Good. Right. Strictly what I did is just the leading piece so far for U, but I will show you that U in general is defined by a differential equation. Okay, so where are we? Good. So let's continue solving. Let's go back now to my equation for R, which I erased, but it's in your notes. Now I'm going to actually Taylor expand that that equation. So, you know, where I have Rn plus or minus 1, I have R of x plus or minus epsilon, where epsilon is 1 over n. And then Taylor expand, keep sufficiently high powers of epsilon, substitute, noise happens, and then send delta to 0 and see what survives, see if anything survives. And indeed, the scalings I gave you will give you some nice things. In the case of k equals 2, let's go back to the equation I had. I had R of x, 2 plus 4g4, 3rx. That's what we had on the sphere before, but now we have some additional terms. It's enough to go to second order epsilon. Dot, and close that bracket is equal to x. Now put the scalings in, and in a couple of lines of algebra, you'll find a very famous equation pops out. This is the Panel-Levy-1 equation. So this is what created all the excitement back in the late 80s, early 90s, 89, 91, whenever those papers came out. The realization that, yes, if I look u of x and I expand in x, I have root of x plus corrections, and I can develop an asymptotic series minus 1 over 24 h bar squared over x squared minus 49 over 1152. Everybody was their heads down expanding equations. This was before Maple and so forth, so people were using the more complicated examples, so early versions of the computer algebra that helps keep track of all of these factors. So this, if I actually then use this, integrate up, get f, gives me the free energy. We get 4 over 15 mu to the 5 over 2 h bar squared plus, well, I don't need the rest right now, but what you hopefully will see, let's do one more term. What you hopefully will see is that this will give you, you can just continue. This is the sphere, counting powers of h bar, or if I were more careful, I would count the powers of h bar over mu to the 5 over 2, but that's going to take me further afield. It's enough to look at the powers of h bar. That's the sphere, excuse me, that's the torus, that's the double torus, etc. But this differential equation contains more. In principle, it contains non-perturbative information, big excitement. Wow, we can study string theory non-perturbatively. So that's where that all came from. That first round of excitement. I want to go much further than this, and of course, many things happened beyond that. So I'm going to jump around a little bit. Let me say a little bit more about why. So yes, why is this what we expect? If you go back to your, KPZ scaling arguments for how the free energy behaves at large area in the theory of quantum gravity.
In the sphere, you're dropping the analytic terms, right? The more
yes.
reading.
Okay, yeah, dropping analytic terms for precisely for what I'm about to say. Thank you. Good. So I have just looking at the behavior I might look for, the non-analytic behavior I might look for to tell me that my area is diverging. I would have free energy. This is in the sort of the continuum theory. So let me use, I don't know, a double tilde or something. The behavior of some bare cosmological constant I might write down, and I would have some dependence like this. So I have some e to the minus mu b times a times some area, fixed area quantity, like that. And then it was known, so KPZ and various other papers, not that KPZ, the other KPZ, Nizhnik, Polyakov, Zamolodchikov, the scaling, how this behaves at large A was known. It goes like some mu, some coupling mu, I'll call mu C to the A times area to some power, which was given by something I'll just call gamma, which depended upon it might be gravity coupled to some conformal system, so it depends on the central charge of that conformal system, etc. So it's some critical exponent. And then you can, that's an equal sign. And then, so this goes something like mu minus mu c to 2 minus this, this fractional power. And so expectation value of A is differentiating with respect to mu and dividing by the thing, so log of thing. And you can see then you're getting a divergence as mu goes to mu c, which is what you want, what we were looking for. And that's precisely the kind of thing we're seeing here. And if you actually observe in the case of pure gravity, which as Igor observed, the case of pure gravity is gamma equals -1/2, and that nicely matches this 5/2. Yes. So mu here is the scaled version. It's the piece that survives mu minus mu c is mu, the mu we're talking about here. So that's the connection. For a unitary theory, for the unitary members of this series, the one unitary member of this series, mu really does identify with the cosmological concept. It's a little bit more complicated when the theory is non-unitary, but it's still some operator in the theory. Okay, time is short, so I'm going to move on from that. But that's a beautiful story, which.
So very
Yes.
those analytic pieces that Igor was mentioning, those would correspond to things that are localized at A = 0. Is that?
Yeah, they just don't scale in a way that can be captured by this. Yeah.
I mean, that's it's at A = 0.
Yeah, so they don't scale. So this argument wouldn't be able to see them. Indeed. Thank you. Okay, so that's a long story, and apologies again. Well, you might be concerned that I just sort of made it up. Right, I just sort of stuck the mu in there. Where did that come from? Well, what I could actually do a little bit more carefully, but I didn't do it at first because it wasn't clear what the motivation was. But now you see what it is. You can see I do have an additional parameter in the theory, and it's G4. And it goes to a critical value, but that critical value should have a scaled piece as well. And that turns out to be mu. So if you work through the algebra more carefully, what you'll see is that you can trade in the mu here for seeing that you have G4 is -1/12 plus a scale bit, and it's minus mu over 12. It turns out to be times delta to the 4th. So had I originally started with this, and then I would have exactly the right number of parameters I have of scaled parameters, you would have been just fine, but you would have wondered why I did that. But now I've sort of identified what mu's meaning is, perhaps a little bit more clearly. Okay, let's move on. So this can be done in general, for general K, and there's all sorts of wonderful things to be discovered. But we must move on. So I promised you that there are a couple of other nice things that happen that organize the problem rather nicely in this orthogonal polynomial language. And one is that there's this quantum mechanics that appears. Let me keep this. And let me just show you where that comes from. You've already sort of seen the pieces, and I already gave you a bit of a warning yesterday. And what that simply comes from is the fact that the orthogonal polynomials are sort of building this interesting system that looks like a quantum mechanical problem, and indeed in the continuum does become just that. So in the same way I did the scaling just now for the equation satisfied by R, as I said, I can consider what happens in equations, in integrals, excuse me, where if you remember, I had my psi n's, which were e to the minus nv/2 orthogonal polynomial divided by root hn. Okay, and these things essentially in integrals look like the kets and the bras that we talked about. So when I take the continuum limit and n goes to x, I have this notation here I would use. And then you could ask, what happens when I multiply an orthogonal polynomial by lambda? So we know what the discrete version of that is. We can ask what happens inside integrals is this. So the point is to track, using these scaling relations, what happens to this thing. And so we go ahead and we do what we did before. We have x plus epsilon. If you go and you look in your notes, you'll see that I'm just writing out the relation, but I've divided, I've normalized and used a couple of relations we've already discovered, and that will be something that you can again expand. Right, this is a shift operator, so you can write it as e to the epsilon d by dx, and you can write this as e to the minus epsilon d by dx, and then you can Taylor expand and expand the exponential and just see what happens. What will happen in a couple of lines, time is short, so I won't do it, but it's a nice exercise, is that this thing will become, well, there'll be a constant piece, which is 2, which is the endpoint that we're expanding around, minus something that happens at order delta squared, which is the piece which ends up surviving the small piece away from the, the thing we would have written as E, right? How much have I deviated from 2, and that is an but now I'm interested in the operator. So it's an operator, and it's h equals minus h bar squared d2 by dx squared plus u of x. And so there's the famous Schrodinger Hamiltonian that appears in this problem, and it's going to be very useful for us in a moment. You can see naturally then that its eigenvalues are going to be E, and that follows through by then following the psi's themselves. I think it actually goes way back to an early paper by Greg Moore, who showed in the case of the Gaussian model that these Hermite polynomials become Airy functions. So in general, these things become, so this is psi n of lambda. So it's it would be psi capital X of lambda, but then in the scaling limit, something pops out, and it's a function of little x and E. And these things then form a nice eigensystem, which is the closed form statement of, it's the complete statement of what are the orthogonal polynomials now, just in the scaled limit where we really care. What are the orthogonal polynomials given some u, which is effectively this is remember the RNs, the recursion relations for the recursion coefficients for the orthogonal polynomial. So in this scaled limit, then, the meaning of this quantum mechanical theory is just to help you define the orthogonal polynomials, which you would then take back to the matrix problem to build things like the free energy and correlation functions, etc. So I hope that makes sense. We're going to use it to learn some very interesting things in a moment. Yes, that's all I want to say about that now. Well, actually, while we're here, now let me use a different board. Let's see what the spectral density looks like in this language. Again, part of the reason this is kind of nice to be able to tell you about this stuff is because I know there's a lot of, it seems very mysterious, right? A lot of papers, most of mine in recent times on JT and things like that, essentially start with this system. And sort of where did that come from? And so now hopefully you understand where that comes from, where it comes from, what it's good for, what it's doing. The important thing then is to understand a little bit about some of the funny formulae that you'll get. So the spectral density when the dust settles ends up being the following expression. And it wouldn't take too long to derive it, but I'm gonna sort of maybe derive it in a different way in a moment. But let me show you intuitively where it comes from. So that's a funny thing to do from the point of view of this quantum mechanics, but that's because this quantum mechanics is just an organizing system. The physics is here. So what's going on? Well, I have this function here, which, if you remember, began life as the orthogonal polynomials. The nth orthogonal polynomial was like the nth energy level for a given lambda. So I need to go and find out what excitations are turned on in all of those sectors and add them up. And that's what this is doing. So sorry. Now I'll say that again, because I just said the opposite of what I wanted to say. I need to go and find out in a given sector, which is at a given E, I need to find out what all the energies are. So that's psi squared for each energy level, which is X, and they integrate over all the energy levels. And that's the integrating up to the Fermi level in the fermion picture. So that's what this means. So
tell us how to normalize psi in this formula?
I will in a moment, because and the way to do it is to connect to perturbation theory. So I'll show you a couple of examples, because we're going to connect back to the Gaussian case in a moment. So hopefully that intuition is clear. There are other things you might build, and a very important one from the point of view of JT gravity is this thing. And this now is going to be a starring object. And again, it looks funny, but now you understand where that came from. Any question I ask in the matrix model will boil down to building it out of something which I will then sandwich between, doing all of the energy sectors, build it out of the Fermi sea, if you like. And so there is in this language precisely this H. And so this is how you might see a lot of this presented. So there's our H, and there's this. And this turns out, Banks et al., this turns out to be the expectation value of the thing that creates loops of length L. If our original matrix was called M, in the double scaling limit, after the dust settles, this is what this is. So it'd take a little bit long to go into exactly how that works, but that's the object that results in the double scaling limit. Correlation functions thereof are rather beautiful in this language. You essentially end up stringing, for example, lots of different Z's. Correlation functions, for example, would end up just stringing lots of these together with an X and a Y and then a Y and a W and a W, right? And then integrating over all of them. And there's some formulae that will make sense in that many body language that I gave you. We'll need only this today. Okay. Right. Time is not on my side. Good. Let's do an example. So going back to our example then, if we go and look, remember R as this. R started out in the simplest example as X. And if you compare that to that, you'll see that U must be minus little x in that simplest example of the Gaussian case in the double scaling limit at the endpoint. So our potential looks like that. Here's X. And now, for simplicity, I can do this at any mu, any value of mu. This particular problem, mu ends up, for reasons that make sense in the topological gravity and lots of other reasons, there's an overall shift symmetry with mu. You can kind of see that integrating up to some value mu. I could undo that by simply changing my variable x, shifting x. It ends up shifting the energies. It's not a big deal. I'm going to set it to 0. That matches with conventions when we build all of the full JT model out of lots of these types of things, and you match to the JT perturbation theory, mu is indeed 0. So I'm just going to do that right at the beginning. So I'm going to integrate henceforth up to x equals 0 from minus infinity. And now I need to know what my wave functions are. Well, if I look at this problem, and that it's just the defining equation of the area function. And so the wave function psi ends up being some number times the area function, and it's of minus e plus x times h bar to the minus 2/3 is the answer, times a constant. And now indeed, the answer to your question, Edward, is if I, for example, just look at the leading behavior of this, which as an area function is just 1 over e plus x to the quarter, and then I must square it. And then this must be, when the dust settles, it turns out to be e to the half over pi h bar. That fixes what this normalization is. And that turns out to be h bar to the n minus 2/3, I think. So you can do that in every case. If this were JT gravity, I know what this would be the Schwarzian, and I can normalize in the same, I'd have some different function here, and I can normalize. So that's
same square root of e.
Yeah, the spectral density derived from the Schwarzian,
So
etc.
you literally normalize the size so that this integral gives the already known answer for rho.
For the leading piece, for the sphere, yeah. And then, so the way to do that, the way to make connection with what we did is to ask what is the W, for any function, for any potential I have here, I can write down the leading WKB form of the wave function. That's enough to tell you a lot. That leading WKB form, if you put it in, you put it into here. Let's actually go ahead and do that. Just quickly, you'll remember the WKB form has a piece that goes like the square root, sorry, the fourth root of e minus whatever the potential is, and then the exponential pieces. So I have that squared. So that's going to end up, let me just put that here, WKB. That ends up giving me an integral minus infinity to mu 1 over the square root of e minus u naught dx. If you look at this, this is precisely up to a factor, which turns out to be 1 over 2 pi h bar. This is precisely the double scaling limit of that representation of the spectral density, that integral representation of the spectral density that I gave you earlier. And then there are corrections to this which are all symmetry, but we'll talk about that in a moment. Okay, hopefully that makes sense. So in this case, this is a rare example. This and some Bessel examples are the ones for which you can write everything down exactly. This, you can write down the full non-perturbative wave functions. And so you can do this integral and get the full non-perturbative physics. So let's see what that is. And this is more or less where we usually, stop when we do non-perturbative physics. So now put this into here, and back it comes with an expression for the spectral density, which is this built out of area functions. And I will just draw the result for you. Okay, so I have E. The leading behavior is e to the half, as we saw, e to the half over pi h bar. And then there are corrections. And let's use this color. When you plot the result, you find that indeed, okay, these wiggles eventually level off, and at large E compared to h bar, they become the classical result. Okay, So two things we learn here. One, it doesn't end sharply when I correct in 1 over n. And if you do the analysis, you see these are exponentially small pieces that can leak out. Famously, those were associated quite correctly with the presence of d instantons in the language, and then later on certain kinds of d branes in the string theory perspective. But let's try and remember that we're just doing matrices. So let's try and understand what this means. This again, I want to emphasize that a lot of the language used here, while not wrong, can sometimes be a little more mysterious than it needs to be. So remember yesterday I said it's helpful when you can to actually just remember its matrices and to do the matrices. Just do the Gaussian sampling, for example. So go back to that data set that you created when you generated the Wigner semicircle law, and now scale into the endpoint. Scale all those numbers you got for the eigenvalues, but just in the neighborhood of one of the endpoints. And you will see that the matrices are indeed doing that. There's as a histogram, you will see that there are these bumps as well. And they mean something, and that's what we're going to get to next. But are there any questions about this? All of this ports over to doing, for example, JT gravity. And a lot of my work in various papers since 2019, particularly mid-2020, where you do the numerics, because these end up being very nonlinear problems. I can show you the analogs of those sorts of wiggles. So this is where we usually stop a lot when we talk about non-perturbative physics in this context. And there's a lot of information in here, a lot of how the spectral form factor is controlled, and a lot of the beautiful calculations that people do need to be aware of this underlying sort of structure that appears non-perturbatively. Even if you can't get all the way down, there's semi-classically, you can get some of these bumps, and there's information there. But one of the things I want to tell you today in these lectures is that there's a lot more information than we've been using. So that's what I want to get to next in the next remaining, I don't know how many minutes I actually have. 15? Oh, that's generous. Thank you. Okay, but are there any questions before I proceed? And I have skipped a lot of things. There's a lot of beautiful work been done even before exploring the area I'm going to explore now. Okay, so the real question might be is what is the origin? What do these bumps actually mean? And typically what we do in our papers is we mumble something about the underlying discrete structure and so on and so forth. But it's really important to make it explicit. So run your data again, right? But now color code, right? Ask every time I generate a matrix according to the Gaussian probability. I compute its eigenvalues, lambda1, lambda2, etc., etc. I bin them, and then I scale into this region, and I see these bumps. Now color code these. Ask make the first ones yellow, the second one's red. I don't know. Pick a color coding, and what you'll see is the following structure. You'll see that these bumps have their origins in the presence of. They're precisely telling you about the probability distribution functions of the first level, or if you like, the ground state, the first excited state. Sorry, that doesn't go all the way up because these must add. And third, fourth, fifth, etc. Okay. Now, if I drew this more carefully, and I've drawn this spectacularly badly, if I drew this more carefully, a number of very instructive things will appear. Will become apparent. What actually happens, let me just try and clean this up a little bit so it looks more like the way it actually is supposed to be. But if you're following along near a device of some sort, please just download my paper and look at the plots. These peaks will persist, but they'll change their character as you get to larger and larger energies. What actually happens is that they begin to get narrower. and they begin to get closer and closer together. The spacing is essentially set by h bar, which is why you don't see them at leading order. And but there's a dependence that means in addition their spacing also shrinks. And I'll say more, I'll write you down a formula in a moment because I'll show you how to compute that. Why is this interesting? This is interesting because it already tells us that the matrix model knows more than we usually say about its contents. This function, the spectral density, which is what we've written down here, is indeed a continuous function, but it also knows about a discrete structure. And I'm going to tell you what I think this discrete structure actually means. So I'm going to give these peaks a name. I'm going to call them the probability of the nth level function of E. And it's a probability peak. Now, I have some notes, which there's no way I'm going to get time to go through it and still talk about the physics. And I 0 for ground state up to infinity. So there's a discrete structure there as well. What I'm going to argue now, or in a moment, is that there's a definite spectrum that this matrix model is trying to tell us about, and I'll tell you why in a moment. But then what you do is you take that spectrum and you insert it into the ensemble, and it gets broadened out by being in the ensemble. And I'll tell you how that works in a moment. So that's where I'm going. But let me just tell you that there's a whole family of techniques that I did not have time to talk about that tells you not just how to do this numerically, you know, by throwing dice and picking matrices, but actually builds these peaks by computing an object called the Fredholm Determinant. And if I had another half a lecture, I would tell you how that works. But all of the things I'm telling you about now are explicitly described with examples in my most recent paper at the end of January. And so you can find all the techniques there. The key things you need is the full non-perturbative description of the theory. You can see this is not something you're going to be able to do in perturbation theory, which amounts, for example, to knowing the size. The key object that you use in all of this is something that is well known in both the matrix model and gravity literature, but perhaps not used very much in the gravity literature, which is the kernel K E E primed, which is integral minus infinity of mu psi x e primed dx. This is a very natural object. Essentially, all probabilities in the matrix model can be addressed in terms of this object. You essentially build everything out of determinants of this object. And so this is an example of what people call determinantal type processes in StatMech, and this object is rather nice. You can use this object to ask questions, to answer questions about what's the probability of the probability distribution of the first level, the second level, the third level, etc. And you can get answers. Time is short, so I can't show you how to do that right now, but I'm happy to talk some more offline. So what are we going to do with this? What's the physics I'm getting at? So I remind you then, I can do all of this, not just for the Airy model, but for any minimal model. And by virtue of being able to construct JT gravity a la the initial suggestion in SSS that you can follow to essentially think of it as a limit of minimal models, or a sum of these sort of KDV frame type minimal models. I can build everything out of the minimal model. So it's enough to tell you what's going on in the minimal models to explain what I think is going on in JT. So in the remaining 10 minutes, let me do that. So there's a very nice tool which is useful Let me just actually show you that. The very nice tool that's useful that tells you something rather nice. It gives you the asymptotic form of the location of those peaks, and moreover, helps confirm something that you might be worried about quite justifiably. Either the average energy of these peaks, or the peak energy, or something that we could read off in a Wagnerian in the Wagnerian spirit that's telling us about some preferred Hamiltonian that we're studying an ensemble of, the preferred Gaussian ensemble matrix. Something about that can be read off from each of these peaks. And one concern a number of people express is that, well, maybe I shouldn't be able to do, what says that there's some correlation between knowing something about these peaks, this peak, and this peak, and this peak, and this peak? And the answer is that, well, this is well known in the random matrix model literature, but also there's an object which is very natural from the point of view of perhaps gravity and string theory, which is the top wave function, which actually turns out to be, and again, not enough time, it turns out to be the FCZT D-brane partition function in one language. But if you remember where it comes from, orthogonal polynomials are essentially, you can think of them as determinant operators. And so it's the expectation value of a determinant operator, which looks like this, lambda minus m, in the double scaling limit times some factors. And the key point here is that this is a characteristic polynomial of the matrix. So the double scaling limit of this is also telling you something about the characteristic polynomial. And its zeros then are telling you about the average location of the eigenvalues of this matrix. So it's actually rather nice to see where those zeros lie. And what you'll see is that they actually track the peaks. Exactly. And so if I had time, I could prove that for you by just seeing how rho is built out of this thing and then tracking where the zeros go. And it doesn't quite get it right. It sort of misses the peak of the peaks. It's a little bit too, it's about there. There are points of inflection on this blue curve, and it lands exactly on the points of inflection. So it's a little bit late. And the reason that's the case is because if you track it through, it's as though it's the determinant of the slightly smaller matrix, the n-1 size matrix. And that's because, remember, when I get to mu, I've used up all the size up to n-1. So it doesn't quite get the answer right, but it gets better and better as I go to higher peak value. And so tracking the zeros of this, which is actually relatively easy to compute, gives you nice closed forms for what that spectrum looks like. So if you work that out, you'll find then in this case, it's just knowing where the zeros of the Airy function are. And so you get a rather nice formula. The spectrum then, asymptotically, is just, and remember, the Airy function that has that leading 1 over e plus x to the quarter, and then there's a cosine or a sine, depending upon your choice of phase, and then you can just read off where the zeros are. And if you read off where the zeros are, you'll get 3/2 pi h bar j, where j is an index 2/3. So here's a really, really important fact. I can actually then ask at what rate are these, what's the density of these peaks, these delta functions, which this would be if I took that single spectrum associated with each peak. And you can see it's just a derivative. You know, it's just dj dE. What's the leading density asymptotically? So if you just do that and see the factors, you'll see that this eventually just becomes, you know, e j to the half over pi h bar. This again generalizes. I can do exactly the same thing, for example, in the case of the Schwarzian, and that's what I would see. So I have this discrete spectrum that gets narrower, narrower, narrower. Let's draw it. The gaps become narrow, narrow, narrow. And by the time I get to the regime where we actually compute the sinh root e times 2 pi over h bar 4 pi squared, by the time I get to that regime, it looks continuous. So this is, for me, a really central point. We start out by deciding that the Schwarzian can't be the complete story because it's a continuous function, and there's no well-defined quantum mechanics associated with some Hamiltonian of that form. There isn't a good Hilbert space, etc. But actually, if I now go back in time and tell you that there exists spectrums, and in fact, a distinguished one that the matrix model knows about, there exist spectra that do exactly what we want from a quantum gravity problem. In other words, at large E here, it becomes the Schwarzian, but actually it does have some discrete structure, and the characteristic, remembering H bar in the case of the JT gravity is set by the entropy of the extremal black hole. This is exactly what we expect that gap to be. And so what I think the matrix model is doing is telling us that there does exist a completion of the Schwarzian. And it is indeed something that if I went back in time before the matrix model picture showed up and we thought the answer was the matrix model is JT gravity, we would have indeed found this interesting. So how does this fit with what we already know and make it okay to proceed perhaps with some new understanding of what the matrix model is really doing? So I'm just going to end by telling you what I really think is going on, and I'll give you the evidence for that. What I really think is going on is the following. There does exist a holographic dual to the problem that we started with. There's ADS. There's ADS with some boundary with beta B, sorry, with length beta, excuse me, with the Schwarzian dynamics, and we got this. Asking for how this thing gets corrected as we go to small e, or if you like, large loops, large beta, was something that we weren't able to do using normal field theory techniques. But I think there's an answer. And I think the answer is that this is the full spectrum. If not exactly to do with the peaks or something, there's some prescription I'm still trying to figure out that tells you that there's how to pick out the energy associated with each peak. But the point is that given such a prescription, there is a spectrum that does exactly the right kind of thing. So that's just field theory, if you like, or however you want to put it. You could then, that's just gravity on the disk. You could then ask, what happens if I put it on topology? Which I think is a separate question. And that's actually then what the matrix model is telling you about. So let me say this in those words now in a different way, just to be provocative, and go, let's imagine, let me write WWWD. What would Wigner do? Let's imagine that we were trying to solve this problem. We're trying to find the dual Hamiltonian, H, but it's a difficult problem. It's big, right? And this is exactly what Wigner did. And Wigner said, well, how about I characterize H as much as possible? And how would you do that? Well, I know that at large E, it becomes rho naught, the Schwarzian. And actually what I'm saying applies to all minimal models as well in this description. So it becomes e to the k minus a half, if you like. Now let me study the ensemble of all such Hamiltonians in order to try and characterize the one I'm really looking for, right, following Wigner. So I study that ensemble. What would I write down? I'd write down the matrix model we first started with. Yeah, and so then Wigner would go, ta-da, the Hamiltonian looks like this. There's somewhere associated with this peak, there's an energy, and so on and so forth. It's a discrete Hamiltonian that becomes continuous and becomes this in the limit. I don't know exactly what it is. I need some other way of computing it, but the matrix model is telling me it exists. That's what I think is going on. Now there's an additional, so this is Wigner. This is the Wignerian way of doing things. But now, because of a happy accident of 2 dimensions, something else happens. We can also expand that matrix model. And if we expand that matrix model a la 't Hooft, we discover something else, which is that there's a topological expansion. And now we see what topology means. It's doing a Wignerian trick in order to make 't Hooft work. It's saying in order to get smooth surfaces at higher topology, I take not just the one dual spectrum, which is the actual holographic dual, you know, the analog of n equals 4 Yang-Mills if this were ADS5. In order to do higher topology, I actually study the ensemble of these. And what that's really doing, it's just filling in the gaps to make smooth objects. And that's what this is. So I take many of these guys, put it together, and I build the blue thing, which is rho of E, the matrix model spectral density. And from that, I can then do topology and smooth geometry. So this is a restatement of, for example, what the spectral form factor is, why it's this nice smooth object coming from averaging over lots of spiky things. It's precisely those spiky things are coming from the discreteness of the spectrum, a single copy of the dual. I look at the correlator of 2 copies of it. It's messy. I can't do that in gravity. So instead I average and I build a wormhole. And that's where topology comes from. So I hope this is just a taste of a little bit of how this works, but I think that's really what the matrix model comes from. And so I think there is no factorization problem. I think holography is safe. It was just rather hard to find this in the same way that if you just played with ADS, you would never have found Yang-Mills as the dual. You really need the full string theory, ADS5 plus S5, brains, all of that stuff. It's a little bit analogous to that. And then you can put Yang-Mills on different topologies and discover interesting things and phase transitions, what have you. And that's somewhat loosely analogous to what I just described here. So that's the setup. Let me end with one last remark. I know I'm really running over. I really apologize. Another way to motivate this is to go back to the minimal models. Everything I said applies to the minimal models, including that simple topological one. So this implies, quite reasonably, I think, that there exists for every one of those minimal models, which after all is just some conformal field theory coupled to gravity, that there should be a complete answer to what is the model on the disk without reference to topology. That should be a well-defined thing. We shouldn't need ensembles there. And so I think there's an answer, and it's a discrete spectrum that in the case of the minimal, I could draw you the generalization of this for the minimal models. There's a nice formula you can write down. And I think that's a very well-defined question. If I were to actually fully compute the Ising model on the disk, for example, I would find that sort of spectrum. And this is the prediction for what that form of the spectrum would be. At the end of the day, I build JT gravity out of lots of copies of that sort of thing. If I don't need an ensemble for those well-defined models, why would I need it for JT gravity? That's sort of probably all I should say at this point. A little bit more time, I would have told you that all the things we do say about random matrix statistics and why it's a good play, why it seems good that they show up because of quantum chaos, that's still true. But it turns out that the deformations and so on and so forth move these peaks around and sample different spectra in a way that's consistent with sampling across random matrix model statistics, giving you the sort of quantum chaotic behavior you'd expect for deformations of the black hole. So it's all there. We haven't been doing anything wrong in formulae. We've, in my opinion, just been misinterpreting some aspects. So I'll stop here and invite you to pelt me with rotten fruit or whatever your response is, but I'm happy to answer questions, and apologies for running over.
Thanks, Robert.
I have a question. Yeah, so either in the minimal string or in JT gravity, we can do the calculation in the disk exactly. And we do find the continuum density of states, either using Liouville coupled to the minimal model or JT gravity. So it looks like you're saying that you should change your bulk theory to, if you want to reproduce this discrete.
I don't know if it's I don't know if it's a change of the bulk theory, or whether there's just something invisible in the calculations you refer to that make them perfectly fine, not wrong, perfectly self-consistent, but somehow unable to be sensitive to the structure that shows up when this is too large. I don't have a good answer to that, but I feel that it's not inconceivable to me that just the purely field theory calculation where everything is continuous just can't see this kind of discreteness at the outset. You just need something else. So one way of doing it would be perhaps to construct some model of D-branes that built the black hole and then compute the Hamiltonian on the world volume, and that would be the way of doing it exactly. And we used to do things like that, but we sort of maybe moved on to other things. So it may be time to revisit the sort of brain building of black holes and taking extremal limits that could construct those Hamiltonians explicitly. Yeah, just one thought. But I think something's been missed by having this field theory right at the outset. Yes.
Well, if we did start with the higher dimensional theory that was derived from string/M theory and is dual to a well-defined CFT, we would have some kind of black hole microstructure and a definite spectrum.
Yeah. We
could also reduce it to JT gravity.
Yes.
We have a certain limit. The trouble is there are many theories in 3 or more dimensions that all reduce to JT gravity. Mm-hmm. They have different microstructure and different black hole spectra. So JT gravity doesn't know which of them you're interested in. Mm-hmm. So it doesn't know which spectrum to give.
That's true. But I think it's important information to know that there is a spectrum, which is what I'm arguing here.
Well, I'm arguing against that. I'm saying there was a spectrum if you start with a particular higher dimensional CFT, but there were many of them. And therefore, there's just no way that the 2-dimensional theory can produce a distinguished spectrum.
I'm not sure I agree. I think the ambiguity you're talking about is going to translate more into the sort of non-perturbative ambiguities I didn't have time to talk about that define the matrix model itself. Once you fix that, then you'll have the structure.
Questions that have structure, but most of us don't think it gives evidence for having a particular distinguished spectrum. What you've written was precisely what you wrote as P of n and e, was the probability distribution for the nth level. Mm-hmm. That was great, but it doesn't tell us that there's a distinguished value of the nth level. On the contrary, you wrote a probability distribution.
No, that's fair. But I'm invoking Wigner and saying that you finish the job of doing the matrix model by actually picking out the characteristics of a given one. And yeah,
Wigner would have said you pick what is the nuclear isotope you're interested in, and it would then give some detailed spectrum, which would be different for each one. You wouldn't claim that to the matrix model we should associate the distinguishing.
True, but he also wouldn't have claimed that the answer is the ensemble itself, right?
Well, in his work, there was the precise. He would have claimed that Random matrix theory can't give more than average answers for nuclear energy.
I completely agree that I have not said that I have not said that the matrix model actually knows how to compute the final answer for that spectrum. I'm saying instead that it's telling us to go back and reconsider because it's clear that such spectra exist, or it's clear to me, in my belief system, that such spectra exists. So there's still a separate problem of now going back and doing the quantum gravity calculation and seeing that the spectrum is there. And I think the matrix model is telling us that it's there and what it looks like. But it's not telling exactly.
I tried to give a reason it shouldn't be there. There are many models in higher dimensions with different answers, which can all be reduced to JT gravity. And JT gravity doesn't know which of those you were interested in.
I think the details matter in terms of exactly how they land on JT gravity, and
but there, the answer maybe that it's not JT gravity, but you have some particular matter content or whatever that is coming from the.
That's what I mean by the details matter. But I think
the bug theory.
Yeah, I think this is giving us the first draft of the. It's telling us of the existence of the spectrum, and it is also giving us the first draft of what it looks like. There will then be details depending upon exactly what embedding gives rise to which. No, I understand you have to. Yeah, but thank you. And I think that's exciting.
You consider the probability, the joint probability for the first two eigenvalues set. So that probability that eigenvalue 1 is at E1 and eigenvalue 2 is at E2. So we know that that's not equal to the product of those of P1 at E1 times P2 at E2.
Sure.
Wouldn't the joint one give you the peaks at different locations?
The things will move around a little bit. I completely agree.
If you do that, if you imagine doing that pairwise for every pair of eigenvalues of 1, 2, 3, 4, etc., that would give you a different spectrum. That could be what you might call another candidate UV completion of the Schwarzian theory.
Perhaps what I would say at this point is that there are two. Let's see. I think I already gave you one strong indicator that associating an energy with each peak is meaningful, and that is the fact that So I don't think that means that there's an argument that says these peaks get washed out in some way along the lines you're saying. Another argument, if I dare be so bold, comes from experiment. Right? People actually build these systems in the lab, and you see the peaks. Right? They're actually physics.
I'm not saying the peaks go washed away. I'm saying they move slightly. That's all.
Yeah, they may move slightly. Yeah, I never claimed that I had the exact prescription. I'm saying that we should reconsider the key thing that has driven us to this conclusion that that you need an ensemble as the dual has been the continuous Schwarzian story. And like I said, if I went back in time and said, hey, actually the Schwarzian is simply the completion of a very particular kind of spectrum. And this is perhaps a little unexpected, right? You may have thought the discreteness should show up and it just shows up everywhere. But no, it does it in this rather clever way. So it hides itself. Any one of these looks like this, and then they all tend to the Schwarzian in a nice way. But then you see how that arises. That H bar arises, setting the gap. And that's rather subtle. And I think that's why we missed that. I think the matrix model is telling us to go back. And there's some other scheme that we missed. Here's another thing that's rather nice along the same lines. You can see then that the when I get to this Tuftian story, when I do this sort of alternative universe where Wigner's trying to solve this problem, writes down the matrix model, gets this and goes, there should be something, okay. And then accidentally there's Tuft, because I can do what I started with at the beginning of the the last lecture, which is to do this topological expansion. It's not accidental then that it is precisely in this parameter, the right parameter that should be, and that coupling in JT gravity has the top, is right in front of the Euler character. It's a beautiful collision of Wigner and 't Hooft in precisely this context. And it's why, in my opinion, triple S appears and why it works. Yes.
Suppose we, if we take, say, the minimal string and we were all powerful and we compute the whole genus and compute like these instant non-corrections, whatever, would you think that in the end, after like all this work, we could get actually discrete spectrum? Or, I mean, I think we still get the wiggly line, right?
You just get the wiggly line. Yeah, you need, yeah.
But so what should you do to the bulk theory to basically get a sharp spectrum?
So it's not
sharp.
Oh, I see what you mean. Yeah.
Then there should be some computation that in principle I'd be able to do in the bulk.
Oh no. I see what you're saying. So again, I think it's, if you define gravity to be the thing and all the topologies, then it is the matrix model.
Yep.
Right? What I'm saying is that the discrete spectrum is the answer to asking what's the dual just on the disk. This is analogous to discovering, by taking limits of branes, that ADS5 with no funny topology in the interior is n equals 4 super mils. So the question is then, what would I need to do to discover what that this actually has a discrete spectrum?
What's an ADS5? I would to reproduce, at least that's what I've been taught. I think that to reproduce the dual like spectrum of n equal to 4 super mils, I would need to sum of all the possible background geometries that are asymptotically ADS5 times S5 and compute the string partition function on that these geometries and sum them all up. Like that in print, like no idea how to do that, but in principle that's what I've been taught, I think.
No, so that to my mind is talking now about not just n equals 4 Yang mills, but all the possible phases you might want to explore, and all the and so that's the analog of not just being at the single spectrum, but mixing in all the other ones as well.
I think the partition function receives contributions from other stuff in the book.
Exactly.
Right? Just the thermal partition function on S1 crosses S3.
I mean, you're basically saying that the thermal partition function of the dual quantum mechanics is a sum of discrete stuff, right? That's the. I hope I'm not misreproducing it.
Yes.
So then there should be some computation I can do in the bulk to reproduce that.
Yeah.
And the conventional ADS-CFT tells me that in principle I should sum of all the geometry. I don't understand why you're saying that somehow this is only the dual of the disk.
I'm saying I guess I'm not saying it very clearly. Partly because I'm still new to it too. There are, what does the matrix model contain? It contains, it's the spectral density that you'd see using the conventional probes that we normally talk about. But my claim is that it contains a lot more, and it knows about these peaks. Right? So what would I need in the conventional language in order to find these peaks, I guess is what you're asking. And that is because the object that I wrote previously, K, which I use to compute the Fredholm determinants, etc., is built out of these things. So it's some sort of thing that sort of knows about these D-brane probes. It's sort of a bilinear built out of those two things, and indeed, then that is the thing that can be sensitive to the peaks.
But there's no bulk. Is there any bulk computation that I could do? Otherwise, I don't understand what the statement is. If you don't tell me what the bulk even is that you're claiming the dual to. That's my main problem. Like you're saying that there's a dual to something like JT, but there's no computation in JT that at least I know to reproduce that spectrum, at least in principle.
No, I agree.
So that's basically your definition of what JT should be.
I think that the calculation you should do comes from doing the full ADS2 cross S2 problem. And so ultimately, I think it's along the lines of what I was discussing with Edward, where you would construct some space-time configuration of branes intersecting with branes of various kinds, and then take the near horizon limit of that, which gives you ADS2 cross S2. And then at the same time, the field theory on the world volume of those branes is a thing in that limit, whose Hamiltonian you can compute. And I think it'll give you this spectrum. That's my answer.
That's your definition of JT.
Well, yes.
I think this is a good point to formally end.
Okay.
You guys can discuss over tea.
Yeah. Thank you, everyone.
A wonderful.